Let's jump right in here and start working on some more integrals of rational functions using our partial fraction decomposition strategy. So, just as a very quick review, I've projected the steps again on the screen, and what we want to do is check to make sure that the rational expression is first in proper form. Use long division if necessary. We will factor our denominator completely into a product of linear and irreducible quadratics. They could be repeated. Then we're going to break that rational expression up into partial fractions using this theory right here in the middle of the board. So each linear factor, however many times it's repeated, we'll get that number of little linear partial fractions, and then each irreducible quadratic will get irreducible quadratic partial fractions. We will set that rational expression that we started with equal to its partial fraction decomposition and clear out the denominators and use algebraic techniques to figure out the constants for each of those partial fractions. So that's our strategy. We talked about finding those constants and using a variety of different methods to do that. And I'm going to show that again in the examples today and on this video. And then once we've found all those constants, then we get into the integration and we use some of our integration techniques to do that. So we take a look at this first rational function. It is in proper form. We have just a constant in the top and degree 3 in the denominator, so we're definitely in proper form, but we're not factored yet. So let's get this thing factored, the denominator, and see what we end up with. So I look at that, I notice that I could pull out an x squared, and then I would have an x minus 9 left behind, and that is fully factored. I took a quick glance, but that is a linear factor. It does not factor any further. So that is fully factored, and now what we have to do is determine what type of factors these are. So it turns out that these are both linear factors, but this is a repeated linear factor. Now that might seem funky because it looks like it's a quadratic, but it is a linear factor, x minus 0. It is just repeated. It is repeated 2 times. So keep in mind, even though, it can be easier to see a linear factor like x minus 2, it's easier to see that that's a linear factor that's repeated, but keep in mind that x is a linear factor. And when we put a power on it, then it's a repeated linear factor. So this is a repeated linear factor, and then clearly this is a repeated linear factor, and this is just a single linear factor, not repeated. So we have two unique linear factors, and one of them is repeated. So when I break this down using that algebraic theory, when I break this down into partial fractions, I'm going to get a over x plus b over x squared. Each repeated linear factor will get the number of repeated partial fractions, the same number of, if it is repeated twice, it will get 2 partial fractions. We will increase the power on the factor in each of the denominators. So those are our 2 partial fractions from the x squared repeated linear factor, and then we have a x minus 9 linear factor, and it is not repeated, so it will create just 1 linear factor. Linear partial fraction. So we have c over x minus 9. So we have 3 partial fractions, and now we just have to find those constants. So this is where we get into the algebra. So let's find the constants. And again, I like to pull this off to the side. I don't do this in the integral. We will come back to the integral once we found the constants and plug those in and then integrate each of those partial fractions. So we'll find the constants. This is a lot of algebra over here, so it's algebra side work. We'll talk about different ways to do it, but we'll take our rational function and set it equal to its partial fraction breakdown. So a over x, b over x squared, and c over x minus 9. Now we're going to multiply both sides of the equation by the denominator. Let's squeeze that in there. It will clear out, obviously, the left side denominator, and then we're going to multiply both sides and distribute it to each of these partial fractions. So I'll write all this in so we can really see what's going to happen and what cancels, and until you get really comfortable working with this, you don't want to lose any factors when you're clearing fractions. So this becomes 3 over, one of the x's will cancel here, so I'll have a times x minus 9. Both of the x's will cancel here, so the x squareds will cancel, and we'll have just b times x minus 9. And over here, the x minus 9 will cancel, and we'll have c times x squared. Now, I'm going to go ahead and work down this column and equate coefficients on both sides. There's also the strategic picking of x's that we can illustrate as well with this example. So if we continue, so let's continue, distribute, and figure out what coefficients are on each of the terms. So we'll distribute, nothing to distribute on that last term. So this, and we have just the constant 3 over here. So this becomes ax squared minus 9a times x plus b times x minus 9 times b plus c x squared. And so then my x squared terms, I've got 2 of them, so I will combine those 2 terms, and the coefficient will be a plus c times x squared. I've got just 2 of those x terms. So those 2 x terms, I will combine those coefficients, and that's going to become minus 9a plus b times x. And then I've got 1 constant term. So minus 9b is my constant term. And that is all equal to, on the left side, just that constant 3. So remember, when we equate coefficients, what we're saying is, okay, so what's the coefficient on each side on the x squared term? So on the x squared term, notice over here, of course it's not written in, because there is no x squared term on the left side. So that means that the coefficient on x squared is 0. So that means a plus c has to be equal to 0. And in a very similar way, negative 9a plus b has to also be equal to 0. So negative 9a plus b is equal to 0. And then the constant, negative 9b, now there is a constant term, it is 3, so negative 9b is equal to 3. And now we've got a system of equations. We use our algebraic techniques to solve systems of equations. We can use substitution or elimination. Substitution is going to work real nicely here because we know from the last of those equations that b has to be equal to 3 over negative 9 or negative 1/3. And then we can just start working our way back up. So then on the next equation, negative 9a plus b, so minus 1/3 equals 0, which means negative 9a equals 1/3 divided by negative 9, and a is equal to a negative 1 over 27. So we've got a, we've got b was negative 1/3. Now we just need to find c, and I'm going to squeeze it in right there. So a is negative 1 over 27 plus c equals 0. So that would mean that c is equal to positive 1 over 27. And I have found my 3 constants to plug into my integral. And I will do that. I want to just show one other possibility, kind of that strategic, so or strategic picking of x. So strategic picking, I want to show how we could use that here to kind of use a combination of what we did with our expansion and system of equations, and also with using the strategic picking of x values. Remember what I'm writing over here. So notice here we were equating coefficients, and here is another way to work that equation that we had 3x times, I'm going to rewrite it, x minus 9 plus b times, the process is still the same to start here. We clear the fractions and we get to an equation where we're looking at both sides of the equation. And then we can kind of strategically look at this and say, well, what would be a good x so that some of these terms on the left side would zero out? And I look and I see that x equaling 0 would be a good spot to start. If x equals 0, then the left side of the equation is just that constant 3 still, but 2 of these terms will cancel out. So this term that has a times x minus 9 will zero out, and c times x squared will zero out. So those 2 terms will zero out, and we will end up getting b times negative 9. Well, that can quickly be solved. Divide both sides by negative 9, and b would be 3 over negative 9, which is negative 1/3. third, right? And again, notice the similarities, right? Like we're kind of working our equation in a slightly different way, but we're getting the same constants. So we got b equals negative 1/3. Then we could pick 9. 9 will also zero out. X equaling 9 if we let x equal 9. So if we let x equal 9, if we plug that in, of course, 3 is still going to be 3 on the left side. If we plug in x equals 9, though, two of the terms, the first two terms, this term and this term will zero out. So those two terms will zero out, and we will get c times 9 squared, which is 81. And then we can solve for c, and c would be 3 over 81, which is 1 over 27. Now, here's the thing. So at this point, what else can we pick? And at this point, we're kind of stuck because there is no other obvious term because of that repeated linear factor. We already used x equals 0, and that zeroed out all the terms. So we still need to find a. So at this point, we still need to find a. We already found it using our other method, so I'm not going to go through that whole process. But what we could do, we still need to find a. So what we could do is we could plug in our b and our c. We could expand and then equate coefficients. So we still need to find a, use expansion. At this point, we know b and c, so we could plug those in, use expansion plus the values of b and c to find a. So I'm going to just leave it at that point. It looks similar to what we did on the left side here where we were expanding, but at this point we already know b and c, so we could plug those in. We can plug b and c in. We can expand and then equate coefficients, and we could find a pretty quickly. So, just these finding of this process of finding these constants is a lot of just work with algebra. And I'm trying to give you guys some tools. However you want to use these tools, it's up to you. You can use a combination of them. You can use always just equate the coefficients and solve the resulting system of equations. You can use the strategic picking of x values, but sometimes we end up in a spot like we did right here, where we've got two of the values, but we still need to find the third or fourth, or maybe the third and the fourth. And at that point, then we can plug our values back into the equation and just play around with it, right? I think of these as puzzles, right? We've got to find however many constants are coming out of our partial fraction decomposition. How we find those constants is up to us, but it involves algebra, often with systems of equations and or choosing of strategic x values. But now that we found them, let's plug those back in to our integral. I'm trying to keep them on the screen so I can plug them in, and then we'll zoom in on the integral. So this is going to become the integral of my a was negative 1 over 27 divided by x, plus my b was a negative 1/3 over x squared, and my c was 1 over 27. So plus 1 over 27 x minus 9. dx. Okay, now, so we found our constants. Now let's get in there and talk about how we could integrate them. And I will say this, we could leave those constants in the numerators right there and just integrate each of these terms by its form. There are actually some pretty basic integrals now that we've gotten it broken down. But I don't really like those constants, so I would actually, just to clean it up, this is kind of a clean up the fractions. So I don't have to carry the fractions on each of those terms. I look at those fractions in the constants there, and the common denominator there is 27, and the numerators are all 1. So I'm going to just factor out a 1 over 27. I'm going to put that in the front of my integral. That will make that just a negative 1 over x. This will become, actually that was a negative, so we were adding a negative, so I'm going to subtract. This is going to become, since I'm dividing, here's a little trick with the numbers there. So we're taking negative 1/3 and we're dividing by 1 over 27. Remember when we do that, right? When we factor something out, a constant like that out, we're dividing by that factor to pull it out. And so what we're doing there is we've got negative 1 over 3. We're really multiplying it by 27 over 1. So notice that the result right there is going to be negative 9. So a little thought bubble on where this number I'm getting is coming from. So when I factor out that 1 over 27, like I did here, and put it in the front, then this negative 1/3 will become a negative 9 over x squared. This was just a 1 over 27, so that will become just 1 over x minus 9. Now, did I have to do that? No, I could have carried those constants, those fractional constants throughout, but this just makes it a little nicer, and I have that 1 over 27 just sort of sitting in the front, and I can leave it there. Now I'm going to integrate each of those term by term. This is going to become 1 over 27. This is going to be negative natural log of the absolute value of x. Now this term right here, this negative 9x squared, remember that's negative 9x to the negative second. So when I integrate that, I get negative 9x to the negative first divided by negative 1. And then this last term, let's go ahead and write that as 1 over x minus 9 dx, so we can look at it individually. When I integrate that, I'm going to use a quick little u sub. U equals x minus 9. My du is just dx, so that becomes the integral of 1 over u du, which is the natural log of the absolute value of u. So I'm going to jump right into that and plug it in. Did that quick little u sub off to the side just so you can see that. 1 over 27 negative natural log of the absolute value of x. This was a negative and a negative, so it becomes a positive 9, and I'm going to drop the x down, positive 9 over x. This becomes the natural log of the absolute value of x minus 9. And we have an integration constant. And, well, technically, I guess we integrated three fractions. There was 3 little mini integration constants, but they all add up to 1 integration constant. And we can leave our answer like that. I did just want to mention that when you have logarithms, so we have negative natural log of the absolute value of x, and we have plus the natural log of x minus 9. And so we can think of our rules of logs. If we have the natural log of a minus the natural log of b, that becomes the natural log of a over b. And sometimes it's nice to combine these and work with these a little bit more compact of a form. Certainly if it's a definite integral, we have to plug in values. So we could leave it just like that, but we could also apply rules of logs. And my rules of logs say that this becomes, let's see if I need to change colors. This becomes 1 over 27. We would end up with the natural log of the absolute value of x minus 9 divided by x, because the negative natural log of the absolute value of x plus 9 over x plus c. So just, one of those things like, do we want to write it that way? If we see it, that might be really handy, but we don't have to write it that way. We could leave it in its expanded logarithmic form, but that's just pulling those logs together. So either of those forms for our solution.